This question belongs to Theory of Computational Subject and was asked in GATE CSE 1991. So the question has two parts. So the first part is given find the number of binary strings W of length 2n with the equal number of ones and zeros and the property that every prefix of W has at least as many zeros at once. Okay, so we have binary string. Binary string means it will have either 0 and 1. Of the total length, we have a W string of total length 2n, such that it has equal number of ones and zeros, which means it will have n ones and it will have n zeros. Okay, and the property that every prefix of W has at least as many zeros and ones. Okay, which means suppose we have a, is this allowed? Yes, as it has every prefix. This has 1 0 and 0 ones, so this is allowed. This is allowed as equal number of zeros and ones. Is this allowed? No, as it do not have equal number of zeros and ones. This is allowed, and every prefix has more zeros than ones. Is this allowed? Yes, equal number of zeros and ones, and every prefix has more zeros than ones. If you carefully observe this and you replace 0 by opening bracket and 1 by closing bracket, then you can easily see that it is nothing but a balanced parenthesis problem. Balanced parenthesis problem. So it is basically asking what are the number of ways in which we can create balanced parenthesis out of total 2n parentheses, or n opening parenthesis or n closing parenthesis. So it is a standard problem equal to the nth Catalan number, which is equals to 2n cn divided by n plus 1. It is nth Catalan number, or it is equal to the Dick-Word problem. It is a standard problem in which we just replace 0 by x and 1 by y, and it is the same problem. So this Dick-Word problem or the balanced parenthesis problem or the given problem all are same, with the answer equal to nth Catalan number 2n cn divided by n plus 1. Now let us see option B. So option B is saying show that all vertices in an undirected finite graph cannot have distinct degrees if the graph has at least 2 vertices. Okay, so which means number of vertices is definitely greater than 2. And let us suppose n equals to 10, and it is saying we cannot have distinct degrees. So what can be a degree? Degree can be 0, 1, 2, 3. Let us try to do it by contradiction. Okay, let us try to do it by contradiction and assume that all degrees are distinct. So we have degrees from, for n equals to 10, we have degrees from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Which means for n, we have degrees from 0, 1, 2 up till n minus 1. Okay, now let us try to plot this graph. If we have 10 vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have a 0 degree vertex. Let us suppose this is a 0 degree vertex. So it won't be connected to anyone else. Yeah, and see, we have a 9 degree vertex too, which means it should be connected to everyone else. It should be connected over here, over here, over here, over here, and over here too. It should be connected to this too, which means we can't have a 0 degree vertex and a 9 degree vertex simultaneously. So we can't have a 0 degree and n minus 1 degree vertex simultaneously. For that to happen, two vertices should have same degree. Should have same degree. It also goes by the pigeonhole principle. You will get the same statement, like, which means all vertices cannot have distinct degrees. Thus, we have proved it that all vertices cannot have distinct degrees by contradiction. And thus, we can say that we can have 0 to n minus 1 degrees can be there, but two of them should have same degree, which means either two vertices with degree 2 or two vertices with degree 0. It is acceptable, but all distinct degrees are not acceptable. So the answer for first part is nth Catalan number, and here we have proved this.